one last example that I'll discuss for now before wrapping up is the idea of then something unnatural, kind of mimicking the categories that I introduced earlier. So if you want to make a molecule that's unnatural, depending on how unnatural it is, you may or may not be able to succeed with what's known in the literature at this time. So it isn't certainly the case yet that metabolic engineers can make anything. But one interesting case of something that is quite unnatural that metabolic engineers can make is propane. So you look at propane or other alkanes, and you see an absence of the kinds of functional groups or even elements in the periodic table that we're used to seeing in nature, especially in nature, at least in natural organism, we don't see hydrocarbons without any kind of oxygenation. You do see, based on geologic pressure and time, alkanes and hydrocarbons like this coming from petroleum. But that's not what we're counting as nature here, because it wasn't a metabolic process that results in that kind of formation. So if we're looking at how can we engineer metabolism to make propane, this is a good example where you might then try to apply some retrobiosynthetic framework. What kind of enzyme would you pick? Or what kind of precursor would this propane come from? And you can perform this kind of analysis stepwise. Now, people didn't really have much of a clue, I would say generally, at least the field, until a few developments. One of those was in 2010, when a team published some information related to alkane biosynthesis. And alkanes are molecules that appear in nature, but at very different chain length. So in cyanobacteria, you'll see alkanes in the C15, C17 kind of range, heptadecane, pentadecane. And that's just much longer than C3. But maybe these enzymes could have broader substrate specificity than what they actually make in nature. Maybe they aren't provided a precursor that would generate propane. And if they were, then maybe propane would occur in nature. Or maybe they could be engineered to act on something that's smaller. And so in fact, there was a lot of data suggesting that some of these variants could act on smaller molecules, and that they could also be engineered to have higher activity. And so what these aldehyde deformylating oxygenases do is they take an aldehyde substrate and then they essentially remove the carbonyl group with a decrease in chain length by 1. So you would know then that in order to get propane, your precursor would have to be butyraldehyde. And then you just kind of continue this process, wondering how you'd work backwards. And in 2014, a team from Europe kind of figured out that, okay, well, butyraldehyde you can get from butyrate. And butyrate is naturally occurring in a lot of different bacteria. But it's not necessarily that simple. Sure, we might know how to go from glucose to butyrate and then toss in, two enzymes. One, a carboxylic acid reductase, the same kind of CAR actually that also is used in the vanillin biosynthesis pathway, to go from a carboxylic acid to an aldehyde. Then you have this ADO gets you to the alkane. But actually, to get the ADO to work well, you've got to work with one of its cofactors and provide some kind of cofactor recycling solution here, which both involves a ferredoxin, oxidized reduced, as well as something to provide a necessary NADPH cofactor, and then here to remove sort of the peroxide that you would get. In addition, you've also got to worry about things that reduce aldehydes to alcohols, which is some competing product and actually where most of your carbon flux would go rather than to propane. So you can see how once you have a retrobiosynthetic design, it can then open up potentially a lot of other kinds of metabolic engineering work that you can do. And in fact, they did demonstrate some propane biosynthesis. This pathway and others related to it tend to be inefficient currently because of rather low activity by the ADO. Just the last thing that I'm going to wrap up with on this topic is that part of the reason why I'm really familiar with this work is that although for the vanillin biosynthesis work that I did in graduate school, I did not focus so much on de novo pathway design, I did for a project around alkanes. And so at the time that these authors were biosynthesizing propane, we were a little bit behind, but had chosen to look at a strategy where we would not just focus on propane, but actually look at alkanes of a variety of different chain lengths. There's C3, C4, C5, C7, C9. And that's because for a variety of reasons, whether it be gasoline or other fuels, you might want to blend or different chain lengths as your major product. And really what we saw was this common theme. Well, if you can get the ADO, which in this case, we were using this PMT variant, to accept something as short as butyraldehyde. I mentioned from the table earlier, you have as their natural substrates, things that are more in the C15, C17 range. So it suggested to us that if we could generate aldehydes from C4 to C10, then we could get these different products. And so we, this other concept that I want to just end with here on retro biosynthesis is this idea of modular design. When you start to think about this kind of framework of, okay, well, so the precursor to an alkane has to be an aldehyde, and then that can come from a fatty acid of some kind, then you can essentially design a set of pathways such that you have different modules. The different modules can be used interchangeably, which is what this modular concept suggests, such that if you want to get to, say, C5 rather than C3, well, then you keep this module the same, but you swap out your fatty acid biosynthesis module so that you get more production, use a different set of enzymes slightly that favor the generation of, say, the C6 fatty acid rather than the C4. And then if you want to get even longer than that, you might find that using fatty acid synthesis pathways are more efficient than, in this case, reversing the beta oxidation cycle, and so forth. And so really, these retrobiosynthesis strategies can be applied not just to making one particular product, but to a set of products if you have an enzyme or set of enzymes that are promiscuous. And sort of key to our ability to design the pathway this way was the fact that our carboxylic acid reductases and our ADOs would act on all of these different substrates if provided, thus making it almost like a funnel. Just generate the right set of precursors using the right precursor modules, and then you can get the corresponding alkane product. So I think that is a good place for me to stop.